Okay, so today I'm going to talk about the connection between concentration and work. And really what's motivating this is that so far in class you've looked at PV and gas expansion, but now we're going to bring this back a little bit more to stuff that might be more reminiscent of what you would see in normal biological contexts. So the first thing I want to start off with is try to get a sense of like the intuition behind non-expansion work. And I think to start with this, I think a good place to look at is the analogy of what happens when you're doing work against the force of gravity. So here, these lines just represent the gravitational force that pretty much any object would experience on the surface of the Earth. And so, for example, if you had some type of really heavy rock or object like this, and you wanted to lift it vertically in the air, the amount of work that you'd have to do is the force that's weighing on the rock and pulling it towards the ground, and multiplied by the distance that you would have to raise the rock vertically. And if you recall from physics, the equation for that is given by force times dr, where dr is just the displacement. And would be the equation for that. And so here what you can see is that the amount of work that's done is kind of proportional to, one, the strength of the force that you're fighting, essentially, and also the distance or the amount that you're trying to move the object. And so when we're considering doing chemical work or working against chemical potentials, you can also think of something like a concentration gradient as analogous to this gravitational field that you'll be fighting as you're trying to move molecules up their concentration gradients. And we'll discuss chemical potential a little bit in more detail later on in the tutor session. But for right now, just remember that if you're trying to move something across a concentration gradient, it's almost like you're encountering resistance in the same way that you would encounter it if you were trying to lift a rock into the air. And in class, you saw that the way to formally calculate the amount of work that's required to move something along its concentration gradient is given by this expression here, where delta U is the chemical potential or the concentration gradient. And dN is the number of molecules that you're trying to move. Anyone have any questions so far? Okay, and so next, I'm going to go over a proof that was mentioned in lecture, and this is really to kind of give us a sense of how we can quantify the amount of non-expansion work that's possible for a system to actually perform if you're coupling it with a given reaction. So first, a lot of this is actually all of this comes from your lecture notes, but I've just annotated it a little bit better in a way that helps me understand it, so hopefully you find that useful as well. So the starting point for the proof will be recalling some of the laws of thermodynamics. So from the second law of thermodynamics, you have that the change in total entropy is never negative. And so that's what allows you to write this expression here. Because even though if you have an individual system in which the entropy change might be either positive or negative, you can always conveniently define the surroundings to be everything that is not the system. And so then when you're thinking about the entropy change for the entire thing or the entire universe, the entropy change will either be zero if it's somewhat of like an equilibrium type process, or it will be greater than zero if it's a spontaneous process. And furthermore, in previous lectures, you've shown from the thermodynamic definition of entropy that you can write the change in entropy as the amount of heat that flows in divided by the temperature. And because we're conveniently defining the surroundings to be everything that is not the system, we can quantify the change in the entropy of the surroundings as essentially the negative of the heat that goes into the system. Because if we're saying that everything that is not the system is the surroundings, then kind of by definition, all the heat that flows into the system has to have come from the surroundings. And so the heat that goes into the system is all the heat that's lost by the surroundings. And that's what gives us this expression for the change in entropy of the surroundings. And then the next thing that we invoke is the first law of thermodynamics. And so if we first look at this expression right here, this is just the restatement of the fact that we've said that for a system, the internal energy is really governed by, number one, the amount of heat that's flowing in and out of it, and number two, by the amount of work that either the system is doing or that the system is, or work that's being done to the system. And rearranging it gives us this. Furthermore, if we're looking at this W term here, we can kind of make this distinction between work that's expansion work and work that's non-expansion. And that allows us to write this. And if we take this a step further, we can kind of recall from previous lectures that expansion work is just PV work, and that allows us to write this. And furthermore, if you recall that the definition of enthalpy is equal to U plus PV, which is the assumption that only holds if you're at constant pressure, which is the assumption that we're making here, then you can further rewrite this as the amount of heat flow that's going into the system is equal to the change in enthalpy of the system minus the non-expansion term of the work. And if we take this result right here, that dq sys is equal to dh sys minus dw non-expansion work, and plug it into here, then we arrive at this expression for the total change in entropy for the surroundings. And then if we bring that to our first equation for entropy, in which we also include the system entropy as well, then we see that all of this must be greater than or equal to 0. We multiply by t, and we arrive at this expression right here. And so first, to give this a little bit of context, in the type of expressions, in the type of reactions and processes that we're going to be concerned with, if we're ever trying to think about the amount of non-expansion work that this reaction is capable of doing, then typically this is something that's going to be a very spontaneous process that has a very negative delta G. And the reason for that is because if you have something that is already like very spontaneous, then that will usually provide the driving force to couple with something that is not spontaneous. So in most applications of this expression, your delta G sys is going to be a strongly negative term. And that's why your W non-expansion work is also going to be slightly less negative. And that's why we can go from this inequality here to this, where we're essentially saying that if you have a given reaction that is has a total free energy change given by dg sys, then the amount of total non-expansion work is kind of upper bounded by the total change in free energy. And to give you an example to make this a little bit more concrete, in class, I think you've seen that the hydrolysis of ATP under standard conditions is about negative 28 kilojoules per mole. In biological context, I think it's more around negative 60 kilojoules per mole. But as a result of that, we can say that the total amount of non-expansion work, like the maximum amount of non-expansion work that is possible, is something like negative 60 kilojoules per mole. Any questions so far? Okay, so then moving on, let's go into some concrete biological examples of this happening. So can anyone think of any type of reaction or process that might need to be coupled to something like ATP hydrolysis? Yeah, it's fine. So a few examples would be like anabolic reactions, which is essentially like building up larger molecules. I think in your lecture slides, you've talked about gluconeogenesis, which is essentially just building glucose out of different components, and also examples of transport processes. So moving something up its concentration gradient. And these are all things that require ATP hydrolysis. So this is a figure from your textbook that I think was also discussed in lecture. And the reason why I'm showing this is that even though we say that ATP is coupled to a process to make it more exothermic or to actually make sure that it happens, the manner in which that occurs is usually kind of very creative and not always super straightforward. So in the case of this maltose transporter here, the situation that you have is you have a higher concentration of maltose inside the cell than you have outside. And as a result of that, you need an active transport to get it into the cell. And so the first stage of this entire process is you have maltose binding to this pink protein. And then once this pink protein docks onto this maltose transporter, then this contact allows hydrogen bonds to form. And that's what induces a conformational change. However, as a result of this conformational change, you will now end up with a higher energy intermediate. And because of the fact that these sites down here support ATP binding, you're allowed to go through another conformational change in which these two sites are then able to come closer together. And here's another figure from your textbook that really shows you at a molecular level what's happening between the individual amino acids that's facilitating this interaction being more energetically favorable. And as a result of this, not only is this intermediate more favorable than this one, but these two sites coming together also increase the catalytic activity of the protein and cause the ATP to be hydrolyzed. And so as a result of losing the third phosphate group, this kind of energetic favorability gain that you get is immediately lost. And as a result of that, you go back to a higher energy intermediate, and then the protein opens up once again, and maltose is able to be released into the cell. And so the takeaway from this example is not really to necessarily know all the steps of this process, but just to be aware that whenever ATP is coupled to processes biologically, it can kind of be done in very intricate or complicated ways. And so just kind of generalizing the ways in which this can happen is important. On that note, there are also very simple ways that ATP can be coupled to make certain processes favorable or spontaneous. So for example, ATP can just be used to add a phosphate leaving group onto a site that can make a reaction more favorable. And that's a much more straightforward way of coupling a process than something like this. And then another example that you went over in class was for ATP synthase. And really briefly, the main takeaway from this process, again, is that even though you have a number of complicated steps, we're doing a very simplified model here in which we're assuming that there is this F state of ATP synthase in which it favors the binding of ADP, an inorganic phosphate. And then there's this F star state that kind of favors the formation of ATP. And the observation that your textbook makes is that you can actually drive the conformational change from the F state to F star state by having a higher concentration of protons on this side of the membrane. And really what the example of the book was trying to highlight is that by tuning the concentration gradient of protons across the membrane, you can shift the equilibrium of this happening. And that's ultimately how ATP is phosphorylated and recycled inside the cell. And if you want to read about this in more depth, about the actual mechanism and the intricacies involved, a lot of this is at the end of chapter 9. And so really quickly, just to go over the worksheet problem. So consider a cell with a voltage of negative 100 millivolts across its membrane. So the outside of the cell is at a higher potential than the cytoplasm. Suppose that there are 3 molecular species, X, Y, and Z. X is negatively charged, Y is neutral, and Z is positively charged. The concentrations of all species are greater inside the cell than outside, assuming roughly equal concentration gradients and transporter efficiency, which species will require the greatest amount of ATP hydrolysis to bring into the cell. And when thinking about this problem, the setup basically is you have 3 species that, except for having charge differences, they're basically the same, and you have the same concentration gradients across the cell, and you're assuming that the transporter efficiency of bringing them in and out of the cell is the same, but we're really just asking for which one of these species is it going to require the greatest amount of work to bring it into the cell. And so the observation to make here is that whenever, if you recall the expression that the amount of non-expansion work is kind of upper bounded by the free energy change for a process, non-expansion work does not only include chemical work, but it also involves electrical work as well. So work against an electrical field. And so just the key thing to note here is that because you have this field of a negative 100 millivolts, meaning that you have a higher potential outside of the cell, it's going to be harder to move a negative charge from high potential to low potential, but it'll be easier to move a positive charge from high potential to low potential. So even though you'll be fighting the concentration gradient for each one of these species for molecule X because it's negatively charged, you have to fight the concentration gradient and the electric field, which makes its transport the most difficult. And so the answer to this question is that molecule X requires the greatest amount of ATP hydrolysis. Okay, so that was all I had. Does anyone have any questions?
Based off of the question, how do you know that it's more positive on the outside? Is that what it's saying? Is like the negative 100 millivolts mean that it's positive outside, or?
Right. So I listed here that the outside of the cell is at a higher potential. And so if you can imagine like the electrode placement to measure the voltage, I guess you can think of it as like the positive electrode would be outside of the cell and the negative electrode would be inside of the cell. And your measurement would basically be that the inside of the cell is 100 millivolts lower in potential than the outside.
Okay, thank you.
Any other questions? Okay, I'll hand it off to the next tutor.
Okay, hello. I'm going to be going over chemical potential, which is the free energy per molecule. You can also say it's the derivative of free energy with respect to copy number. And this notation here means that temperature and pressure are fixed and that we're holding all the other types of molecules constant besides the one we're interested in. Another way to think about this is how much does free energy change if I add one more molecule of type I And so the chemical potential will be approximately equal to delta G over delta N sub I. And our delta G is going to be final minus initial. And so that's going to be G, and that's for one molecule. So units are going to be energy per molecule. If we want to look at moles, we're going to have N sub I equal the number of moles of the type I molecule. And so it's molar. So now we have a bar, and it's going to be the derivative of free energy with respect to the moles, and units are energy per mole. And what you'll see in your book and in lecture, we're going to drop the bar because we assume that we're talking about moles. Okay, and we can also rewrite this here. So big N sub I is the number of molecules of type I, which equals Avogadro's number times the moles, right? So if we multiply these out, we're going to get a number of molecules. And so when we rewrite this expression for chemical potential, we can get this this expression here, and you can see that they're equal because these cancel out. And then this term equals Avogadro's number, and so we can see that this is the final expression you're left with, and so that's the free energy of an Avogadro's number of molecules. So next I'm going to explain an example from the textbook and go over the derivation for that. So we're going to start with a chamber with another chamber inside it with holes so that the molecules can move through. And it's going to start with a higher concentration in the inner chamber. And spontaneously, the molecules will move out down their concentration gradient. So we can also say that they're flowing down their chemical potential gradient. And why does this happen? So at equilibrium, this is our equilibrium condition over here. The change in free energy is 0, so G is at a minimum. So this, for example, right, if this is your graph. And so with constant temperature and pressure, we can get this expression for dG. So and this equation comes from, you can rearrange the equation for chemical potential by this here, right? So we substitute in, and we also know that if a molecule leaves the inside and it travels to the outside, then the number of molecules inside the chamber has to decrease by the same amount that the number of molecules on the outside increases. And so we also have this equality. And now that means we can substitute this. And so when we substitute this in and then we factor out dN in, this is what we get. And for this equation to always be 0, this term has to be 0 because this can be a non-zero term. And so what we are left with is this. And this is equilibrium. Okay. Any questions on that? Okay, so yeah, so in our picture, we see that now the chemical potentials are equal and the concentrations are roughly similar. So for a system not at equilibrium, what happens? The change in free energy is going to be less than 0 as the system proceeds towards equilibrium. So the same equation we had before, but now the equality is less than 0. And when this happens, you can either have this term being negative or this term being positive or vice versa, but they need to be opposite signs so that the equality holds true. In other words, you can have number of molecules flowing in negative, and so so the chemical potential inside is greater than the outside, or you can have it the other way. And so we can see that molecules move spontaneously from regions of high chemical potential to regions of low chemical potential, because when we're having molecules float inside the chamber, then that means that the chemical potential is greater on the outside. Any questions? Okay, so something to consider too is an ideal dilute solution, which is where the solute is so dilute that solute molecules don't interact with each other. So the energy of interaction between a particular solvent molecule with other solvent molecules does not change with solute concentration. This means that changes in the chemical potential of an ideal solution as a function of concentration are due to only changes in entropy and not enthalpy. And we'll see how this applies later. And for an example, at physiological conditions, your solvent will be water, and that'll be 55 molar, and your proteins or other things floating in your cells will be millimolar or micromolar. So this is a good approximation. Let's look at this equation now. So chemical potential is proportional to the logarithm of concentration. So here it is, change in chemical potential equals RT ln C2 over C1. And this equation makes sense because we just saw that chemical potential is higher at higher concentrations. So let's look at another example from your book. So this is, imagine this is a ton of grid boxes, and we have this solvent in blue, solute in red, and in each region, the number of grid boxes is going to be the same because it's the same volume. You have more solute in region 1 than region 2, and in each case, your number of solvent molecules is going to be way greater than the number of solute molecules. It just doesn't look that way in the picture because I didn't draw like a million boxes. And yeah, so the number of solvent molecules is going to be the same in both regions because they have the same volume because it's a dilute solution. In other words, if you add more solute, then the solvent concentration is still going to be the same. So to start, we have our Gibbs free energy equations for each region, so H minus Ts. And when we substitute this expression into our equation for chemical potential, with respect to the copy number of the solute in each region, then we get these, right? So it's just the chemical potentials for each. And when we take the difference of these to find the change in chemical potential as we move from 1 to 2, then we end up with this. And the reason that you don't see enthalpy anymore is because enthalpy is the same in both regions because enthalpy is independent of the solute concentration. And so when you subtract this, these are going to cancel. And so now we only see the entropy term. And that means to find the change in chemical potential, now we have to calculate entropy. So since, remember that we have M grid boxes in each region and assume that there are many, many grid boxes. So we can use the probabilistic definition of entropy. So each grid box can be in one of 3 states. It can be empty, it can have a solvent molecule, or it can have a solute molecule. And so the probability of it being empty is the number of empty over the total, which is the total number of grid boxes minus the sum of the solute and the solvent over the number of grid boxes. Similar equations for solute and solvent. Something to note here about the probability of the solvent is that it does not depend on the number of solute molecules. So when we plug in our probabilities for entropy, then we see that we don't see the probability of the solvent molecules because we're taking the derivative with respect to the solute molecules. So it doesn't matter here because it does not depend on it, right? So if you plug everything in, this is what you get for each entropy. And your textbook goes into how to get this equation here. But, so you can look into that if you like. But here we have the concentration in 1 is going to be the number of solute over the volume, same for 2. And then the number of grid boxes is going to be proportional to the volume with some proportionality constant alpha. And so when you substitute these things in, then this is the equation you get, and then you end up with our final equation here. And now we can see that if the concentration of 1 is greater than the concentration of 2, the log of C2 over C1 is going to be negative, and so that means that the change in chemical potential is negative. And now when we look at the equation for the change in chemical potential, you see that the chemical potential in region 1 has to be higher. Okay, any questions? Okay, that is all I have then. So the next tutor I go.
Hi, everyone. Can you see my screen?
Yes.
Okay, thank you. Okay, so I'm going to be talking about chemical potential and the equilibrium constant. So everyone's probably already seen the expression for the equilibrium constant, right? So you know that it's some ratio of concentration. That's probably something you've seen in high school or probably Chem 1A. But so how is it that we can relate the equilibrium constant to the concept you've been learning about, right? So we define equilibrium constant at a point where the delta G of the reaction is equal to 0. We know that equilibrium constant is some ratio of concentrations, and we can express a relation between free energy and concentration using the concept of chemical potential, right? So Gibbs free as the equation that Ryan just gave. So now to derive the formal, to do the formal derivation of the equilibrium constant, we have to kind of put these 3 pieces together. So first, we can just simply express an arbitrary reaction, right? So all your reactants with their stoichiometric coefficients added together in equilibrium with all your product species and their stoichiometric coefficients added together. It's just a fancy notation just to generalize everything and make it more concise. And at equilibrium, using the constraint that free energy change is 0, we can express this in terms of chemical potential, right? So I want to remind you that chemical potential is really just a way of saying, let's say, molar free energy or free energy per mole. So if I take the free energy of each product species times the stoichiometric coefficient of that product species and add it all together, that free energy should be equal to the free energy of the reactants. And that's the same thing as saying delta G equals 0, because if you subtract this, if they're the same, they should equal 0. Does anyone have any questions up to this point? Okay. So now I just want to remind you that this is the expression for chemical potential of a species I. So you could have, this is accounting for if you have many species in solution, right? So you could have 1, 2, 3, up to I species. The chemical potential of the ith species is a standard chemical potential plus RT ln A sub I, which is just the concentration of the ith species. And this is the equation that Ryan went over before. So now all we do is just take this equation and we substitute it into the chemical potential for the reactants and the products. So now we just have this expression, which is still saying the same thing, that the free energy of the reactants equals the free energy of the products, meaning that the change in free energy is 0. So now we've kind of converted our free energy expression into an expression that uses concentration of the species. Does anyone have any questions up to this point?
This is assuming equilibrium, or?
Yes. So we're deriving the equilibrium constant. So everything now is assuming equilibrium. So if it's not equilibrium, this expression right here doesn't hold. It's only at equilibrium that this expression holds.
Okay, thank you.
Question?
Yes, yeah, of course. Thank you.
Yeah, sure. Okay, so after we have that, right? So we have the free energy of the reactants, free energy of products. So now what we're going to do, we're just going to rearrange these terms. So this circle with the bar through it means this is your standard chemical potential. So now in the next step, we arrange all the standard chemical potentials on the left side and all the non-standard concentrations on the right side. So as you see here, this M sub K, mu sub K standard, this is your standard chemical potential of your products minus the standard chemical potential of your reactants. And that's just another way of saying the standard standard free energy change of your reaction, right? So if you have the standard free energy change per molecule of your reactants times the stoichiometric coefficient, of your products times the stoichiometric coefficient, minus the standard free energy change per molecule times the stoichiometric coefficient of your reactants, that's just your standard free energy change of the reaction. So we can redefine the left-hand side as your standard free energy change right over here. And on this side, if you guys remember your log rules, the sum of the logs equal to the log of the products, right? So you can just imagine this whole expression as ln k, where k is just the, on the top, it's just the products of all your concentrations raised to the stoichiometric coefficient. And on the bottom is the concentration of the reactants raised to their stoichiometric coefficients. So we can define the logarithm of this equilibrium constant to be the right-hand side, or part of the right-hand side. And now if we just write everything out more concisely, we have standard free energy change is equal to negative RT times the natural logarithm of your equilibrium concentration, where we define the equilibrium concentration to be this expression over here. Equilibrium constant to be this expression. Does anyone have any questions about the derivation? Or even notation? I know some of this notation might be new for those of you who are unfamiliar with it. And just for reference, I took these expressions off of Wikipedia because I think they had a nice, concise way of writing it out. So if you guys want to look into that more deeply, then you guys can just go and look up equilibrium constant on Wikipedia and it'll be there. Okay, so if no one has any questions, I'm going to move on to discussion of the units of equilibrium concentration. So if you just look at this expression over here, if the sum of your exponents in your numerator doesn't match up the sum of the exponents in the denominator, it might seem as if you have more concentration units on the top than you do on the bottom, or vice versa. And you might get some sort of units of the equilibrium constant, such as concentration to the third power or concentration to the -2. But in reality, the equilibrium constant doesn't have any concentration units. And the reason for this is because when we use the expression for chemical potential, the concentration we use inside the natural logarithm has the value of concentration, but no units, because we divide by the standard concentration of just 1 molar. So if we divide a concentration by a concentration, that gets rid of the units, but the standard concentration is just 1, so we maintain the same value. So when we plug in those values into the equilibrium constant, the units cancel out. So regardless of your exponents, your equilibrium constant will be unitless. Does anyone have any questions? Okay, I will move on. So here, I just wanted to talk briefly about the relationship between the equilibrium constant and the Boltzmann distribution. This was something that was briefly alluded to during Professor Korean's lecture. But I think this is a really useful concept that will help you in the upcoming lectures. So I just want to give you a preview of this. So you guys learned that free energy or standard free energy is able to predict what your system will look like at equilibrium. And that's a concept that's also alluded to by when you calculate statistically the different microstates, the different states. So how is it that these two are related, if at all? So let's imagine we have a system with two states. For example, A is in equilibrium with B, or a folded protein is in equilibrium with an unfolded protein, right? What will the equilibrium constant look like? And how can we express that statistically using the Boltzmann distribution? So we only have two states, and the stoichiometric coefficients are 1. Then the equilibrium constant is just, okay, let's take unfolded protein, concentration unfolded protein divided by concentration of folded protein. That's analogous to saying the probability that your protein's unfolded divided by the probability that your protein's folded, right? And if we account for the energy difference between those two states, you have this Boltzmann factor. But because there might be a number of different configurations between unfolded and folded, there's only one configuration, but unfolded, you could have many configurations. The probability has to be the relative probability of those two states, disregarding the number of configurations, has to be multiplied by the number of configurations for both states. So if we want to kind of bring this back to free energy, we want to express this ratio of multiplicities, which I remind you is just the number of microstates of the unfolded protein or whatever two system configuration you would like. The ratio, you want to express this in terms of the change in entropy, right? Because we know that the free energy is expressed as delta H minus T delta S. So how do we do this? Well, you just use your standard Boltzmann equation right here, right? And then the change in entropy is just equal to the difference between these two. You can do some math and you rearrange and you get this, and we plug it back into this. So this expression is equal to this expression, and you multiply it out, remembering your exponent rule. So you just add the exponents after you multiply this by t, you get this. And this is very close to your free energy, right? So here we get a delta U minus T delta S. Your free energy is delta H minus T delta S. So if you guys remember from the previous chapter, chapter 9, this is the Helmholtz free energy. But since we're just really dealing with concentrations, and Helmholtz free energy is just constant V, and there's really no or almost no pressure volume work for incompressible liquids, and since we're dealing with concentration of liquids, we can just hand wave and say that this is basically free energy. So what we see here is that the equilibrium constant, when we express it statistically for a two-state system, is identical when we derive it statistically to how when we derive it for chemical potential. And if you don't really like catch this, because this was definitely not talked about during lecture explicitly, that's completely fine. This is more of a hint for the upcoming lectures, and I think it's good to see ahead of time so you kind of fit it into this framework. If you don't get anything else, maybe remember that the equilibrium constant is really just a Boltzmann distribution of your standard free energy. Because the usual equation that's showed to people is this equation, that your standard free energy change is equal to negative RT ln of equilibrium constant. This equation is a little bit random, like you can't really intuitively guess your way here. But if you think about the equilibrium constant as a ratio of probabilities between two states, and since you guys have been doing so much Boltzmann stuff in the past, then you can kind of guess that it intuitively makes sense that your equilibrium constant is really just a Boltzmann distribution of your free energy, standard free energy. Does anyone have any questions? Okay, if not, I will pass it on to the next tutor.
All right. Hey, everyone. So I don't have that much time. I'm going to try to finish by 6 o'clock. But today I'm going to talk about the reaction quotient Q and some biological examples using it. So we can define our delta G. This is in your book. We can define it in terms of the stoichiometry of whatever reaction you're looking at. Imagine this is like A plus B is going to C plus D. So these are stoichiometry. And then multiplied by the chemical potential that Ryan talked about, We can define it in terms of that and some reaction coordinate here. And at equilibrium, delta G is equal to 0, of course. But in the cell, normally biological reactions aren't going to be at equilibrium. They need some driving force in one way or the other. So our delta G is actually going to be non-zero for the most part. And the point of this is to say that when we talk about spontaneity of a reaction, we don't talk about our delta G at standard state, which is delta G naught. We look at just delta G of the reaction. So no naught is present. And that's because we need to account for the concentrations of the reactants and products at the reaction we're looking at. So it's a little bit like Le Chatelier's principle. If you have too many products, the reverse reaction will be favored. So that's what delta G without a naught here will tell us. So let's look at a little bit of derivation. I ripped this off Professor Savage's slides. Sorry, it's a bit messy. But we have our delta G here in terms of first our delta G naught, which is what this is equivalent to. And then we're adding on this extra term. So this extra term is using the concentrations that you're observing in the system. So if you're just looking at the system, what's the concentration of the product? What's the concentration of the reactant? That's what we're defining as Q. So we're adding on this extra term and we get this all important equation, delta G is equal to delta G naught plus RT ln Q. This equation allows us to calculate the delta G of a reaction. So we're adding something to the standard state, and now we can calculate delta G depending on what concentration the products and reactants are. So just get familiar with this equation. It's going to be very important for this unit and future ones. So let's talk about Q and K a little more. So we have something called the mass action ratio, which is just the ratio of Q to K, just another way of examining the system. And we can do that by also looking at this graph here. So remember at the bottom here, delta G is equal to 0. That's at equilibrium. So let's look at this now. So if you have a Q less than K, that means you're on the left side here. You have a lot more reactants than products. Your forward reaction will be spontaneous, trending to equilibrium. If you have Q greater than K, you're on the right side and your reverse reaction is favored. And if Q is equal to K, that means you're at equilibrium and your delta G is 0. Pretty straightforward. Just make sure you don't mix those up when you're doing any calculations. And again, you just need to account for the relative concentrations of reactants and products in the system you're looking at. And make sure, remember, just delta G is what we're looking at to observe the spontaneity of the reaction, not delta G naught. So this is just to get you a little bit more familiar with using this equation, something I was confused with for a little bit. So we're looking at this equation. So for these observed concentrations, let's first plug in the standard state concentrations. Can someone unmute themselves and tell me what standard state concentrations are for any species?
1.
Yep, good, 1 molar. So we plug in 1 for Q here, we get an ln of 1. That's 0, right? So this whole term cancels out. So when we plug in standard state concentrations, we're left with our delta G equal to our standard free energy change. That's, like a model form. That would be if you took products and reactants at 1 molar, drop them into the system and just let them go. That's the free energy change you measure, your delta G standard state. Now let's plug in equilibrium concentrations. So if these observed values were at equilibrium, this term here would become KEQ, right? Because it's equilibrium concentrations. So this is now RT ln KEQ. And remember that delta G naught is actually equal to negative RT ln KEQ. So negative term, positive term that are equal, they cancel to 0. So at equilibrium concentrations, if you observe those, you have a delta G equal to 0. And that's our definition again. So that's just to get you comfortable with using the equation and give you a reference for where equilibrium and standard state is. All right. All right, so now let's look at a biological example, which is ATP hydrolysis. Shown here, ATP, you hydrolyze the terminal phosphate to get ADP in a free phosphate. Very important to the cell. So at standard state, its delta G value is negative 28 kilojoules per mole. So that's a negative value. That means forward reaction is spontaneous. So in theory, if you just had ATP and ADP in some concentration in the system, all that ATP would be used up for the most part, right? So you'd eventually reach equilibrium because it's the forward reaction is favored, and then at equilibrium, you would stop. You wouldn't have any free energy change driving anything. So how does the cell get around that? It does it by holding the concentration of ATP and ADP constant, and that's what we call steady state. So those are always constant. That way, it won't ever get used up, and you'll always have a constant delta G value. And just so you know, that ratio of ATP to ADP is around 1,000. So by holding it around 1,000, it actually increases the free energy change to negative 57 kilojoules per mole. That's much more favorable. And that's favorable enough to drive uphill reactions, which we call energy coupling. I'm not sure if you guys talked about that yet, maybe in the future. But just know that's how ATP is driving reactions in the cell. All right. And then this was just a side note. You haven't gone over this yet, I don't think, in class, but we can also describe acid-base equilibria using the same concepts. So if you have an acid here, protonated, going to a deprotonated form, we can describe it using this equilibrium constant, the acid dissociation constant, and then we can do all this fun math here. We can get the Henderson-Hasselbalch equation out of that. So in class, you'll talk about that in a lot more detail and define a lot more terms, but I just wanted to introduce that real quick. pH, we can treat as a sort of equilibrium. So does anyone have any questions? Oh, I got through that a lot faster than I thought I was going to. All right, so let's just do one quick example problem. So there's this made-up molecule, A34G-P, -P representing a phosphate group, has a delta G standard state of -5 kilojoules per mole, and it has a hydrolyzable high-energy phosphate. So I'll give you a minute or so, but can this molecule act as a major energy currency of the cell? And if so, what conditions must be met? So take 30 seconds to a minute, think about it, and if anyone wants to try and answer it, please unmute yourself.
That delta G there, is that for when it hydrolyzes the phosphate off like ATP?
Sorry, could you repeat that? Kind of cut out for me.
Sorry, that delta G, the one that's right there, there's the -5. Is that for when you hydrolyze that A34GP?
Yeah, so you're hydrolyzing one phosphate. And this is
Okay.
I'll give it about 15 more seconds. Okay. So does anyone have any ideas?
I don't know if this is right, but I was thinking maybe it wouldn't be able to act as a major currency because from what we know from class for ATP, that was -28, and this seems just like much smaller than that. So that's what I was referencing towards. So I would say it's not a major energy currency of the cell.
Yeah, I think you're definitely on track with that. It's a very small delta G. So this is the answer I put, but you're right, it is very small. So in order to maybe make that more favorable, it could increase the concentration of the unhydrolyzed to hydrolyzed form. So that way, maybe at that point, you would get a more favorable delta G. And then maybe you could use it for a energy currency. But yeah, good job. And the other part of the answer I was going for is, like ATP, you got to hold it at steady state such that once this reaction starts, it's not going to get used up and stop. Yeah, good job. So that's all I have. Does anyone have any questions? All right, so I guess we're good.
Okay, everyone, I'm going to stop the recording now.